Welcome to my talk on exploring the possibility of a hipSYCL-based implementation of oneAPI. This paper is the result of a collaboration between myself and my students Balint and Holger, all from Heidelberg University. My name is Axel Alpay. So oneAPI is an open specification for a platform built around SYCL 2020 as programming model, accelerated libraries such as oneMKL, for example, for plus operations, oneDPL, oneDNN and others, and low-level building blocks such as level 0. There's a reference implementation led by Intel using the DPC++ SYCL implementation, and there's also a port to NVIDIA mainly led by Codeplay using the DPC++ CUDA backend, and very recently also a HIP backend to DPC++ was added, which paved the way for an AMD port. Independently of this, in 2020 we announced a different idea. We announced that we were going to form an academic center of excellence together with Intel at Heidelberg University, with the idea that we could use hipSYCL to run oneAPI code on AMD GPUs, NVIDIA GPUs and CPUs. And this brings us to the motivation. So using hipSYCL to run oneAPI code, we would be using a different compiler than DPC++. And clearly being able to use multiple independent compilers brings benefits. For example, users can test their code with multiple compilers. This can reveal bugs in user code and also the implementations. It can also reveal ambiguities in the specification. So the key question that we're trying to answer is, can oneAPI actually be implemented with a compiler that is not derived from DPC++? So we're attempting a proof of concept implementation using hipSYCL. And to our knowledge, this is the first attempt to implement oneAPI completely independently from DPC++. When can we actually conclude that oneAPI can indeed be implemented with hipSYCL? Well, clearly, if we look at the various oneAPI components, we need to somehow check that those can work with hipSYCL by implementing some representative portion of those. So for the programming model, we can say that SYCL 2020 must be reasonably well supported, common code must compile, and it should be able to deliver a decent amount of native performance, let's say 80%, and native performance being something like CUDA or HIP. Then if we look at libraries, oneAPI libraries must be implementable with hipSYCL, and we demonstrate this using the oneMKL plus domain. If we look at building blocks, then level 0 must be supported, and to this end we should add a oneAPI level 0 runtime backend to hipSYCL. Let's now dive into hipSYCL in a bit more detail. So hipSYCL is a multi-backend open source SYCL implementation. hipSYCL is designed to integrate with and write on top of various already existing toolchains. It consists of three main components. A compiler component, which consists of the SYCLcc compilation driver, as well as Clang LLVM components that might be used depending on which compilation flow you're actually using. A runtime library, which does things like device management, task graph management, scheduling, and so on. And lastly, something that we call libkernel, which is a multi-backend header library that can be used inside kernels. So this is if you call some SYCL functionality from your kernel, then you would be calling into libkernel in hipSYCL. And libkernel provides things like math built-ins, atomics, group algorithms, and so on. hipSYCL supports multiple kinds of compilation flows. hipSYCL supports library-only compilation flows, for example, using our openMP backend, where you can use any openMP compiler to compile SYCL code to some output binary for CPU, or also using our new NVC++ support, where hipSYCL can operate as a library for NVC++ CUDA support, and then run on NVIDIA GPUs and CPU. Then there's also the option to use this Clang-based compilation flow, where hipSYCL aggregates multiple Clang toolchains under a common roof, and you can, for example, also use the Clang host pass and accelerate compilation for the host using special additional compilation passes that hipSYCL brings to accelerate CPU performance. We distinguish integrated multipass and explicit multipass. In integrated multipass, the underlying compiler manages multipass compilation for host and device. For example, we just tell Clang compile this for CUDA, and then Clang would do a host compilation pass and a device compilation pass for CUDA, and then give us some host binary. Whereas in explicit multipass, hipSYCL manages multipass compilation by itself and also takes care of embedding the resulting device binaries into the host binary. hipSYCL provides a multi-backend runtime based on plugins. Currently we have 4 backends for CUDA, oneMP, HIP, and also a new level 0 backend that I will talk about more in a second. And the idea is that in hipSYCL, the SYCL headers actually construct a function object that we call a kernel launcher. And this kernel launcher is then passed to the runtime, which invokes it when it wants to launch a kernel. And this means that since the SYCL headers provide the kernel launchers and the SYCL headers are compiled with potentially a compiler that supports CUDA language extensions, for example, we can, for example, also use those extensions to launch kernels, such as CUDA's kernel launch syntax. The experimental setup that we will be using in this work is as follows. So we're using hipSYCL 092 with Clang 13, DPC Plus 2022-01, ROCm 4.5, CUDA 11.6, and we're using an AMD Radeon Pro 7 and a GeForce GTX 1080 Ti. Let's first look at level 0. As it turned out, it was fairly straightforward to integrate level 0 into hipSYCL's runtime backend model. So we just had to implement all the hipSYCL interfaces and map those to level 0. Some parts of the libkernel library are still unimplemented, such as group algorithms or reductions, but that's not really relevant to determine if it's possible to run hipSYCL with level 0. What you see here is results of hipSYCL running Babel stream on an Intel UHD 620 using the new level 0 backend, and the performance shown here is relative to the DPC++ performance on the same hardware. And as we can see, hipSYCL delivers performance that's very, very close to DPC++. Now let's look at the programming model. hipSYCL supports many SYCL 2020 features. See, we cannot really cover all of those in this paper, so we can only take a look at a selection. So what we'll be doing is we'll be looking at 3 features: unified shared memory, USM, group algorithms and subgroups, and also optional lambda kernel naming. For USM, let's first discuss some terminology. Traditionally, the buffer accessor model was the way of managing memory in SYCL. USM has introduced an alternative pointer-based model. In explicit USM, explicit data transfers are necessary whenever you want to move data from an USM allocation between host and device. So you need to invoke some memcopy function. In shared USM, however, this data migrates automatically, so you can dereference a shared USM pointer both on host and device, and it will just automatically migrate data as needed. This is similar, for example, to CUDA's unified memory. We will be looking at the parallel research kernels benchmarks, because those provide memory benchmarks for multiple models, in particular CUDA, HIP, and SYCL, but they also provide the SYCL version in multiple variants using shared USM, explicit USM, and also the traditional buffer accessor model. And what you see here is the performance on the NVIDIA GPU normalized to the performance using CUDA with NVCC and explicit memory migration. And as we can see, for all results are very close, and there's not really much of a performance difference if you use buffers, or if you're using SYCL or CUDA, or if you're using shared or explicit USM with SYCL. If we look at AMD, we again see very similar performance between hipSYCL and HIP, except one thing stands out, and that is that shared USM in particular is performing poorly on ROCm in general, but that's the case both for HIP and for hipSYCL. So this is a performance issue in ROCm, not a hipSYCL issue. If we look at how performance between USM and buffers compares, we see that if we decrease the problem size, we start to see some performance gap between USM and buffers, where USM outperforms buffers. And this is because buffers may have a slight additional overhead, which can be noticeable if you have short running problems. In hipSYCL, buffers internally use explicit USM pointers anyway, so buffers just add an additional layer on top of that. And with buffers, the runtime has to do automatic dependency analysis, automatic data migration with buffers, which in the USM explicit USM pointer case, the user does basically. Don't take away from this that USM is always better, because it's not. It's just that in hipSYCL, for very short running problems, there's an additional overhead for buffers. Now let's look at subgroups and group algorithms. So subgroups are group types below the granularity of workgroups. And in hipSYCL on GPUs, those are mapped to CUDA warps or AMD wavefronts. Group algorithms in SYCL 2020 are algorithmic primitives that exist both at the subgroup and the workgroup level, such as reductions or scans. We contribute a benchmark suite that's open source, and you can get it at this link, that contains micro benchmarks to measure group algorithm performance for the various algorithms described in the SYCL specification for various data types, and it also supports native libraries such as NVIDIA's CUP or AMD's ROCprim to compare SYCL performance to native performance. What these benchmarks effectively do is they measure the runtime of a kernel with some number of workgroups, and each workgroup basically just invokes the tested group algorithm for 512 times. If we look at the NVIDIA GPU, if you look at inclusive scans, we can see that for workgroup sizes of 128 and 256, hipSYCL performs very competitively with the native CUP performance, both for Clang and for NVC++. If we look at the AMD performance, again, depending on which group size you're using and which algorithm in ROCprim you're using, again, you see that performance is generally very competitive. Things change a bit if we look at reductions. For reductions, hipSYCL is considerably slower, both on NVIDIA and also on AMD. And the reason for this is that reductions are a fairly simple operation. And this means that any kind of instruction overhead you can notice in these kinds of micro benchmarks. And in this case, we get instruction overhead in the SYCL version because the group size in SYCL is not known at compile time, while CUP and ROCprim expect the group size as a template parameter. So they know the group size at compile time. And you need to know the group size because depending on whether the group size is divisible by the subgroup size, for example, you can implement those group algorithms in different ways. And that means that in the SYCL version of the benchmarks, there's effectively an additional if statement to check this. Now, there are mainly three ways to work around this issue in a SYCL implementation. One is JIT compiling for a particular workgroup size as soon as you know it. This does not work well with hipSYCL because hipSYCL relies heavily on ahead of time compilation. Then the second option is multi-versioning, so you can compile the kernel ahead of time for different group sizes. That's also difficult to implement in the library-only compilation flows that hipSYCL supports. And lastly, there's also attributes in SYCL, such as required workgroup size, that the programmer can use to specify the workgroup size that will be used. But again, of course, in library-only compilation flows that hipSYCL supports, we cannot add any custom attributes. So one solution is a programming model like hipSYCL's scope parallelism extension. And this model allows implementations to instantiate kernels with different group types and can also then encode things like the workgroup size in the group type. And this allows it effectively to do some kind of multi-versioning with pure C++ template semantics. However, I'd also like to put a question mark at the relevance of the group reduction performance for real-world applications, because if we are already dominated by instruction overheads of an if statement, basically, then it's likely that for most kernels that are not exclusively executing group reductions, maybe the performance difference might not be noticeable. Now let's look at optional lambda kernel naming. In SYCL 1.1, you had to explicitly give each kernel a unique kernel name, so that the host compilation pass and a device compilation pass could agree on a common name for a kernel so that the host could call the right kernel from the device binary. In SYCL 2020, this kernel name became optional, so you can just directly call your parallel 4 without having to provide a kernel name. And this is, of course, a massive convenience improvement. However, it's highly non-trivial to implement in a multipass scenario because C++ does not define unique names for lambdas. In hipSYCL integrated multipass, this just happens to work because then we can leverage the support for similar feature in Clang CUDA toolchain and the Clang hip toolchain. In explicit multipass, we have to implement this functionality ourselves, and to do this, we are leveraging the built-in get device side mangled name built in from the Clang hip and CUDA toolchain, which allows us to obtain the mangled name of a kernel function in the host pass, as it would be mangled in the device pass. This, however, cannot really work in the NVC++ flow for non-CUDA, non-CPU targets, because NVC++ does not have this built in. So what is the practical impact when we actually try to transition oneAPI code from DPC++ to hipSYCL? To this end, we are looking at HeCBench, which is an open source benchmark collection that contains over 280 benchmarks gathered from various sources. And those benchmarks are provided in multiple programming models, in particular, including hip, CUDA, and SYCL. And the SYCL ports, importantly for us, were originally developed for DPC++ and oneAPI. And that means that we can investigate performance compared to native models and also investigate potential portability issues when moving from DPC++ code to hipSYCL. So what we found is that 209 benchmarks work out of the box with DPC++, 91 work out of the box with hipSYCL. Those that did not compile, however, mainly did not do so because of recurring fairly simple problems. For example, there's a specification ambiguity in SYCL with regards to the use of the legacy CL/SYCL HBP header. HeCBench uses this header and the top-level SYCL namespace. The SYCL specification, however, is ambiguous here, whether this header should expose the top-level SYCL namespace or whether it should expose CL-SYCL exclusively. In hipSYCL, CL/SYCL-HVP exclusively exposes the CL-SYCL namespace. If we fix this, then the number of compiling benchmarks goes up to 114. Then there are some benchmarks that use functionality from the SYCL extension oneAPI namespace, even though it should actually be in the regular SYCL namespace, such as atomic ref. And fixing this again increases the number of compiling benchmarks to 122. Then there's an interesting issue because in hipSYCL, vector aliases such as SYCLflow2 can collide with CUDA types, which also defines a flow2 type, but in the global namespace. So if you're using the namespace SYCL, if you're opening the namespace, then you can get name collisions. This can also happen if you're using DPC++ and you're in a CUDA interop scenario, so you're including some CUDA headers, then you will be having the same problem. Then there are some benchmarks that are opening both the SYCL and the STD namespace, and this can then cause collisions for things like a standard queue and SYCL queue. Then there are some non-standard APIs that are being used, such as subgroup shuffle, which apparently exists in DPC++, but it's not in the specification. And then, interestingly, there are also subtle differences in implicit conversion behavior, for example, in the VEC constructor. And this boils down to C++ being complicated. The implicit conversion behavior in C++ can depend on if a function is implemented as an overload or using templates, and these subtle implementation differences can make a difference. So how can we address those issues? So for the namespace usage, we could have some best practice guide and maybe some spec clarifications. The non-standard APIs should hopefully become better as implementations mature and fully move to SYCL 2020. The implicit conversion behavior, that's a bit more unclear. Maybe specification clarifications, but those would probably be fairly massive. So overall, the good is that most issues are not due to lack of functionality in hipSYCL, but due to fairly simple recurring issues. But the bad message is that the fact that even basics like header and namespace usage already cause issues, I think that's worrying for the SYCL ecosystem as a whole. If we're now looking at performance for HeCBench benchmarks, namely nbody, MD5 hash, RSBench, and XSBench, and the performance results are again normalized to the native models, so to CUDA using NVCC for NVIDIA and to HIP for AMD. We can see that for all those benchmarks, hipSYCL is within 20% of the native model, except for RSBench, where hipSYCL actually outperforms HIP by 3 times, probably because something is suboptimal in the HIP version of this benchmark. Let's now look at libraries at the example of oneMKL. We have upstreamed support for oneMKL Plus using hipSYCL with NVIDIA GPUs and CPUs. We've also upstreamed a new ROC Plus backend for hipSYCL to oneMKL. And we've also an open pull request for a ROC-RAND backend for the RNG domain of oneMKL. oneMKL mainly requires backend interoperability, so it effectively tries to call optimized backend libraries such as Q+ or ROC+. So it stresses the ability of SYCL implementations to expose native backend objects from SYCL objects. And what we're doing is we're leveraging hipSYCL's enqueue custom operation extension in the implementation of this support, because this has been shown to outperform SYCL 2020 host tasks for the purpose of such interoperability operations. What we are seeing here is performance results on GTX 1080 Ti for matrix multiplication, matrix vector multiplication, and an XP operation. So we have level 3, level 2, and level 1 plus operations here. and we have results for CUDA, so that's basically Q+, then oneMKL using the DPC++ CUDA backend, and oneMKL using hipSYCL. And what we see is that the oneMKL using DPC++ is affected by a performance bug that was causing a constant overhead in runtimes, which was only fixed recently after the submission deadline. So now that it's fixed, the performance is comparable to the Q+ performance, similarly to hipSYCL, which also is very competitive to the Q+ performance until very small problem sizes. If we go to the AMD GPU, again we see that hipSYCL is competitive with the native ROC+ performance, and both oneMKL with hipSYCL and ROC+ seem to show an overhead of around 10⁻⁴ seconds. So in conclusion, we have shown the first attempt to implement oneAPI independently from DPC++. We have shown that hipSYCL can support SYCL 2020 oneAPI building blocks like level 0 and also oneAPI libraries at the example of oneMKL, and also still deliver competitive performance. Therefore, we conclude that it is indeed possible to have a multi-compiler ecosystem for oneAPI. However, it's not all that simple. There are spec ambiguities, some design differences between implementations, non-standard APIs that client code might use, and maybe some best practices are not super well known, and all those things can hinder portability in practice. So overall, portability across implementations still requires explicit attention by the programmer. Alright, that's it. Thank you for your attention.